So yeah, keeping m fixed. So we apply induction on n keeping m fixed. So thing I have to verify the result first of all for n equal to 0. We have 0 plus m plus plus is equal to m plus plus. This is just coming from the definition. By definition, we can write by definition using definition number, etc. But here it's understood that I am using the definition of addition of natural numbers. Okay, so with that understanding, I have written by definition. And what is the other side I have when I put n equal to 0? And 0 plus m plus plus is also equal to m plus plus. This is also by definition. Why is that so? Because 0 plus m is equal to m. Hence, 0 plus m plus plus is equal to 0 plus m plus plus. So this identity is true for n equal to 0. So this is the best case of my induction. Now assume n plus m plus plus equal to successor of n plus m for some natural number n. For n, then okay, now I have to verify the result for n plus plus in place of n. So n plus 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 m plus plus. Okay, that is the left hand side when I have successor of n in place of n. Then this is equal to, or I think I should do the calculation in the center so that I can write show the reasons for the steps or the justifications. N plus 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 m plus plus. This is equal to n plus m plus 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 plus. How am I getting this? This is I am getting from definition. Okay, you think of m plus plus as a single natural number. It is, but you think of it as an entity. Then adding the successor of something to that thing means you add that thing to that thing and take its successor. So here my reason is by definition. That's the justification for this step. Now in place of this one, I am going to write this one. So I have n plus m plus 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 plus, and this is coming from the induction hypothesis. by the induction hypothesis. Okay, now I have to carefully get this expression when I have n plus plus in place of n. Okay, so if I write n plus 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 m, what have I done here? Here I am again using my definition of addition of natural numbers. Adding the successor of something to a natural number is this. So by definition, and this is equal to, okay, is this what I had to show? Yes, this is what I had to show. See, I need not go any further. This in this formula, if in place of n I take n plus plus, then I get this now. So that's what I have proved. So that means I have carried out the induction step successfully. So this completes the induction. And the proof, and hence the proof. Okay, so I have achieved this result also. These two lemmas have taken me somewhat closer towards symmetry or towards commutativity, to be more specific. Now finally, oh, but before that there is one more. Why to is it really necessary? Because we have already seen this. The exercise asks this: why do we have n plus plus is equal to n plus 1 as a consequence of these two lemmas, lemma 2 2 2 and lemma 2 2 3. It's a question. We have already seen this. You remember when we calculated this thing, n plus m, or and what I'm trying to say is this: n plus 1. Oh, no, I cannot say this like that. Okay, let us just solve this y exercise. Since I don't have commutativity yet, see, I also got confused. That's why these things need our undivided attention, because I started assuming that n plus 1 is equal to 1 plus n. I don't have that yet. I have to prove it. So here what the exercise asks us, it asks us to prove this, and it says that this comes out as a consequence of these two lemmas that we have now proved. Let's just see why. What does the second lemma tell us? I mean, among these two lemmas, it says that n plus the successor of m is equal to n plus m, its successor of n plus m. Now here, if we put m equal to 1, m equal to 1 or m equal to 0, m equal to 0, okay, if in this, that means in lemma 2 to 3, in that equation, I am specializing with the value m equal to 0. What do I get then? On the left hand side, I have n plus 0 plus plus, which is nothing but n plus 1. On the right hand side, I have n plus 0 plus plus. Now n plus 0 is equal to n, so I get n plus plus. And why is n plus 0 equal to n? This is coming from lemma 2 to 2. So that's why this identity is a consequence of these two lemmas. That is, the successor of n is n plus 1. I confused this with this identity, 1 plus n equal to n plus plus, which we initially obtained like this. This one comes only from the definition of addition of natural numbers. This one, however, comes from these two lemmas. You see how strange it looks. Simply because in my mind, 1 plus n is equal to n plus 1, so I thought this y exercise is unnecessary. No, it's not unnecessary. It does not come from here. It needs these lemmas. Okay. So now, having gone through this, now we come to the main proposition. So that's why this is proposition. See, I have already said that logically there is no distinction between lemma, proposition, theorem, corollary, things like that. These just indicate the level of importance that these results have. Each one of them is a result. A lemma is an easily proved result whose proof is not very difficult and which comes before proving some result of more importance, some central result. Lemmas are used in the proof of important results. So, for example, if I have a subject in mathematics, if I have a topic in which there is a central theorem or central result, the proof of which may be pretty complicated and runs long, then the proof can be subdivided into some smaller results, some steps, which may individually be proved, each one of them, as lemmas. So that's how lemmas come. So having seen these lemmas, now we move on to the proposition. It is proposition 2 to 4, and it has its usual title, addition is commutative. Addition is commutative. We are now going to prove this, but first we need to state the result for any two natural numbers n and m. We have this n plus m is equal to m plus n. This familiar result will now be proved. Okay. So proof. Here again we are going to use induction. Same. We apply, starting is same. We apply induction on n, keeping m fixed. So first we need the result for n equal to 0. We have zero plus m equal to m. This comes from the definition. And m plus 0 is also equal to n. This comes from lemma 2, 2, 2. This is where we need lemma 2, 2, 2. Hence, 0 plus m is equal to m plus 0. We have the base case for our induction. Next, same, assume our induction hypothesis. Assume n plus m is equal to m plus n for some natural number n. Okay? Then we need to prove the result when n is replaced by its successor. Then n plus 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 m is equal to, see, by definition this will be equal to n plus m plus plus. So this is by definition. By definition of addition. But according to our induction hypothesis, n plus m is equal to m plus n. That I will use here. So in place of n plus m, I write m plus n. Okay. By the induction hypothesis. Right? Okay, now what? Now I will write in place of this m plus n plus plus. How is this legitimate? This comes from lemma 2 to 3 by lemma 2 to 3. So that's why we need these two lemmas in the proofs of this proposition. In the proof of this proposition. That's why we proved them first. So this completes the induction. And we have commutativity. And the proof is over. Now we know for sure that n plus m and m plus n are same. Despite having these those awful expressions for 5 plus 3 and 3 plus 5, now we know for sure that 5 plus 3 is equal to 3 plus 5. Without going into the sequence of incrementations. Without looking into those things, we now know for sure that 5 plus 3 is equal to 3 plus 5. And in fact, for any two natural numbers n and m, their sum is the same irrespective of the order in which they are written. Okay, so we have achieved commutativity of addition. Okay, so then next naturally associativity comes. Proposition 225. Addition is associative. Addition is associative for any three natural numbers a, b and c. We have a plus b plus c. I just want to see how it's written. This one on this. It doesn't matter which way I write which one, but I don't want to miss the steps of the induction. This we have. So here also we prove. Now you see here we have three variables, but regardless of the number of variables, I am going to induct on one variable keeping the other two fixed. So we apply induction on C, keeping A and B fixed. By the way, how to decide which variable is will be convenient for induction? That depends on how the proof goes. It happens that for C this is particularly easy. It may not be so easy if you apply induction on A. You have to figure that out in advance and then come up with the proof. Okay. In this case, C appears to get the job done quickly, keeping A and B fixed. We have, so naturally now first of all we want to check the result for C equal to 0. So the left hand side is A plus B plus 0 equal to A plus B by, just to show that these things, we are not just blindly writing these things, they depend on the previous result. We are going to refer to the results by lemma 222. I think that is the one. Lemma 2, yes. And A plus B plus 0 is also equal to A plus B, because B plus 0 equal to A, B plus 0 is equal to B, again by that same lemma. So A plus B plus 0 is equal to A plus B plus 0. That means our associative law equation is true for C equal to 0. This is our base case. Next assumption, you assume the induction hypothesis. So you see that all these results that we are going on proving by induction show that induction, that fifth hypothesis or the fifth assumption in Peano's axiom, that is how important that is. And the proofs have the same nature to them. So initially they will be very easy, but as we develop more and more number systems, things will become more and more complicated. At the same time, things will get complicated, but we will be more equipped to deal with those things because we are also going higher with our knowledge of these things as we go along. Next, assume a plus b plus c is equal to a plus b plus c for some natural number c. Then a plus b plus, now in place of c we have to have its successor. This is equal to a plus b plus c and its successor. This is by lemma 2 to 3. Okay. Now by induction hypothesis, in place of this I can write this a plus b plus c. This comes from the assumption we have made by the induction hypothesis. Okay. Now we have to have a plus b plus c plus plus. So for that, what we shall do, I can write this as a plus b plus c plus plus. Here again what I am doing, again I am using lemma 2 to 3 if you look carefully. Because I am adding a successor to a natural number. Okay, so that's why just like here I have added the successor of c to this natural number, I am adding the successor of b plus c to this natural number, and the expression comes from lemma 2 to 3. Once again I will apply this lemma inside a plus b plus c plus plus. So now you see a plus b, in place of c I have c plus plus here, and in place of in place of c I have c plus plus here, in place of c here I have c plus plus. So that means I have proved the result for the successor of c based on the assumption that it is true for c. So this completes the induction and gives me associativity. Okay, so I have proved addition is associative also. Okay, now because of this result, it does not matter how I put bracket in a sum. So now this expression a plus b plus c is meaningful. Whether I write it, I first add a and b and then to that I add c, or whether I first add b and c and to the sum I add a, it does not matter because they ultimately will give me the same result. So a sum like this has meaning. Okay, it is not ambiguous. It does not depend on the way we use, we use brackets. Okay. Next comes proposition 2 to 6. Okay. Now what proposition 2 to 6 says? Its name is cancellation law. It's something we keep using. If for three natural numbers A, B and C, we have A plus B is equal to A plus C, then B is equal to C. So this is the cancellation law. We cancel A from both sides usually. Usually means all the time. When we come across a situation like this, we cancel A from both sides. And that is the cancellation law. Now keep in mind, while something like this is encountered, the fact that we cancel one from both sides is justified like this. I said it once, I am going to say it again. Because 1 plus A is equal to 1 plus B. So if I add minus 1 to both sides, then the results are going to be the same because the initial numbers were same. So if I subtract 1 from both sides, that also will give me the same value. Now minus 1 plus 1 is what? 0. 0 plus B. Note that we are not cancelling. Okay, we are just writing the result for 1 minus 1, which is 0. Now 0 plus some real number or something is that real number itself. So this is how we justify cancelling the same term from both sides of an equation. But now we cannot use such a thing to prove this result. We cannot write minus A on both sides of this equation to cancel A. Why? Because minus of some natural number is not available to us. We are yet to see what subtraction is. We don't know. And we also don't know about integers. We only know of natural numbers, and we have introduced only actually two operations, but since this is primitive, something very at the base, so it's not really considered as an important operation. I mean, it has lost its value. I should not say lost its value, but it's gone in the sense that it has been superseded by addition. And that's because in place of n plus plus, now I can write n plus 1. So the use of this notation now falls by the wayside, and it's taken over by this more familiar notation, addition. Okay, so that only we know. We don't know anything about minuses or integers which come from minuses to 1, etc. To 1, these things we already know, but the additive inverses, the negative counterparts of natural numbers, they are still unknown to us. That we will see only when we develop the integers. Okay, so this strategy will not work here. In fact, this cancellation law, when we prove it without any subtraction or this thing, this will eventually help us define subtraction when we introduce the integers, because it kind of allows a virtual subtraction even before subtraction is defined officially, because in place of this, when I write this, in some way I have subtracted a. It gives a sense of subtraction, and this will be used in defining subtraction. So we will prove this using our usual way of using addition. What I'm saying, not addition, the principle of mathematical induction, the fifth axiom. So the proof just follows the usual path. We apply induction on A, keeping B and C fixed. Okay. If so, for A equal to 0, first of all, we have to verify the statement. Okay. By the way, here we are not dealing with an equation or anything. Here we have an implication. You see, it's a statement of the form P implies Q. Or in other words, you can write it like this: A plus B equal to A plus C implies B is equal to C. So to prove an implication, you have to first of all assume the hypothesis and then show that the conclusion is true. So here also we have to assume the hypothesis. That too,